And we are live here with the next talk at Meetings 2025. This time it's Johan Vanslembrouck talking about why use coroutines for asynchronous applications. Looking forward to your talk. Please take it away, Johan.
Thank you, Jans. I'm going to read this slide because it's the goal of this presentation, so it should summarize what we're going to see in this one slide. So what we're going to do is using a variety of examples, ranging from simple to more complex. I'm going to compare three programming styles: synchronous one, using a synchronous input-output API, an asynchronous style, using asynchronous input-output API, and then the coroutine style, which is using the same asynchronous input-output API. And I want to demonstrate that coroutines allow writing applications that are exhibiting asynchronous behavior, but using a synchronous programming style. So combining the advantages of both styles, which means the easy to write, read, and maintain synchronous style with the efficient non-blocking execution of the asynchronous style without introducing any major disadvantages, apart from the learning curve, of course. Now, to make it more concrete, this is an example that we will see further in the presentation, about in the middle of the presentation. And I'm going to use it as an appetizer. So on the left, you see the synchronous style. We just have a function calling three remote operations. So you have the remote operation. Do you see my cursor, Jens? So we have one operation call, a second operation call, a
Yes,
third
I see.
operation. Sorry?
You asked if I see your cursor, and I just
Yes.
wanted to say that yes, it's
It's okay. It's okay. Okay. Thank you. Uh, so we have three remote operation calls, which are all synchronous. That means when you call this operation, it's going to block until the answer have arrived, and then function one can proceed. So we have three calls over here, two of which are going to be called because there's an F in the middle. So suppose this one takes 2 seconds and the other take also 2 seconds, means function one is going to be blocked for 4 seconds. That means the function calling function one is going to be blocked again for 4 seconds and so on. Maybe that's not what we want. On the right, we have the coroutine style, which is very similar to the one on the left. There are a few differences. As you will see, they have been indicated in yellow. So coroutine is going to return a special type of object, async task in this case, with an integer, like we have the integer over here. You have the co-await here, and then instead of return, we have a co-return. Also, the operations we are going to call, the syntax is very similar, but the implementation of this one on the right is going to be asynchronous. So what's going to happen? You're going to call remote operation one coroutine dot op1. This is not going to block. It's going to start the operation and then return immediately so that this one can return control to the calling function or the calling coroutine. The same for the other twos. So here we're not going to block. We're going to pass control back. You could say it's kind of jumping out of the coroutine. And then we're going to jump in again when the answer has arrived. But the style is going to be, well, very similar to the style on the left. So there's not much to do if you want to turn an synchronous function into an asynchronous running coroutine. Now, if we want to do it without coroutines and we want the same asynchronous behavior, we will see there are different ways of doing it. This is one way. So I have rewritten the code, making it asynchronous. So nothing is going to block, but you see the code is very much different and much more difficult to read, in my opinion. There's more than one style, so I have an alternative that's placed in the middle of the presentation, but there are many more alternatives with the asynchronous style than with the synchronous style and with coroutines. So you see, I want to have this style with this behavior, and it can be done with coroutines. So that's the essence of the presentation. Now this one is This example is used as an appetizer. I hope you lose your appetite yet. Otherwise, I would say with the French expression, tant pis, it's a pity, but we're going to continue anyway with the presentation, but step by step. So we're going to start from the beginning and then move on until we see these slides and even more slides. A little bit about myself. I only signed contracts with two companies. First one in 84 and then in 98 to start with Altron Europe in 99. So I've signed contracts with two companies, resigned only once, but I had in fact projects with in total 18 different companies, 16 different clients as consultant, and even multiple projects at the same client with some years in between. I've been studying and using C++ coroutines since June 2019 in combination with various asynchronous communication frameworks. The first one was Boost in 2019, then I added Qt 5 in 2021, gRPC 2 years ago, DAO, ROS2, and so on. Why? Because coroutines, I find them fascinating, and I didn't want to become obsolete before my retirement date. Unfortunately, I didn't have the chance to use coroutines in client projects, but I did see some opportunities. But okay, it's something that takes time to introduce. Uh, you can decide if I have become obsolete or not, but my retirement date is 1 May of next year. And after that date, I will have more time to amuse myself with coroutines. This presentation is in fact an evolution of a presentation that I first gave 3 years ago, but I have given it already at multiple clients, 3 clients in total, in fact 4 clients, with the dry run of yesterday included at my current client. And the previous version of the presentation was at the Belgium C++ user group in January of this year. Since then, that presentation was 68 slides. It has grown considerably to 128. The 68 slides I could fit into 1 hour. So what means that with those 128 slides, I will have to skip more slides than before. So that will be the biggest challenge for this presentation. What I have added in between January and this are more slides about projects that were let's say the inspiration for everything that I have written here. So during those 40 years, 41 years, I've seen projects that could have benefited from using C++, coroutines, except of course that they were not available yet. So I'm going to refer more to these real world use cases, and I'm going to be going less into technical detail than I did before. That's the agenda. There's an introduction to C++ coroutines, 13 slides, then something about synchronous and asynchronous programming, because the title mentions both of them. And then the big part is about why use coroutines for asynchronous programming. Then also why not to use coroutines, and then summary and conclusions. So let's start about C++ coroutines. I'm not going to go into detail into those 13 slides because some of the things that are in these slides I'm going to present more in detail in the third part. This is an introduction I want to give because it reminds me of my early years as a student. So a definition that I found on the web, a coroutine is a generalized routine that in addition to the traditional subroutine operations call and resume, supports suspend and resume operations. So instead of having 2 operations, coroutines have 4. Now we have the term subroutine over here. It reminded me of Fortran, so I've put a piece of Fortran to the right, where you literally find the word subroutine, and you literally find call operation, and you literally find a return. So the return you can still find in C and C++. The call is, let's say, more or less implicit. But you see, we have those operations that are explicit in Fortran. We also have the explicit term subroutine in Fortran. And so That's what I wanted to tell. About the name coroutine, it fits well with subroutine, while in C++, if you use the term function, maybe they should have used co-function instead of coroutine, because uh, coroutine goes with subroutine and function goes with subfunction. But that's my opinion. Now the next slide talks about how do you recognize the C++ coroutine. That's something we have already seen in the first slide with the co-return, the co-wait. There was no co-yield on that one. And also we've seen a special return type. Uh, it's not just end or void or double. It was, in that case, a sync task with end as a template parameter. Also, C++ standard only defines low-level mechanisms to define coroutines. So you have to write your coroutines yourself. And so there's not a standardization yet. This is explain why in some presentations you will find task as a return type. In my case, it's async underscore task, which was originally derived from async space task from C sharp. So this explains the origin of the name. Now, talking about co-functions that we don't have in C++, it's called coroutine. It's something I found, in fact, 23 years ago, and it's called dynamic C. At that moment, I was looking into cooperative multitasking for a client who had developed a cooperative scheduler. And then I found something on the web, and there's a link to the manual called Dynamic C. And Dynamic C has co-statements and co-functions. So that would be a natural complement for functions, and also slide statements. And if you look what they have, slide statements correspond more or less to threads. Co-functions correspond to the coroutines that we have in C++ now. And co-statements are something more parallel. So if you, I don't know that language in detail, but it's so surprising to me that in 2002 there was already something available with the C style. So it must have been around since the end of the 90s or even earlier. So that was and it's still around. You can still find the manual. So that you could say it's an early adapter of coroutines because the concept is very old. It's from 1958. But so there was potential to implement it already much earlier than now in C++, like it has been implemented already in C Sharp and Python and many other programming languages. These figures we're going to see in more detail, or I'm going to explain them in more detail when we come to the third part. They are more meant for people who read just the presentation, so it's a step introduction uh, to the diagrams that I use. What you will see is that we have blocks, functions, they are or coroutines, they are blue blocks, and then you have the call operator and the return operator here. Because we have functions, we just have call and return. This is an exercise just showing if you have virtual functions, it's a little bit more complex. We have more indirections than with functions, of course. Next one is coroutines, but that coroutine behaves like a function. So it has synchronous completion. Uh, Synchronous completion and asynchronous completion, as in the next slide, don't confuse it with synchronous and then asynchronous input-output. That's something different. Synchronous completion just means that uh, you could say the coroutine behaves like a function. There's only going to be a co-return in the last coroutine. Now, something I want to stress, this what you see here. Uh, I'm going to start coroutine 3. It's going to return an object of task of type task. In my particular case, it's going to be called async task, but anyway. And then later on, we're going to await that co-wait that t. Also, so there's a separation between starting your coroutine and the co-waiting. The advantage is that in between the starting of your coroutine and the co-wait, you can do different things in which you don't need the result of the coroutine yet. So that's something I wanted to do. It was not available with Boost ASIO because you could not split the co-wait into two parts. So you had to do co-wait coroutine 3 and not split into these two lines. Also, what you see here is that the coroutine tree is going to start immediately. So that's what they call uh, an eager start instead of a lazy start. A lazy start would only start the coroutine at the co-wait. That's all I want to tell about this because I found it important that I could do this, split it into two parts, and it's going to be more clear later on. That's already with asynchronous completion where we have the resume. First, of course, we have to suspend over here. So this one is not ready with the response. It's going to suspend. The suspend is going to propagate to the original caller. And then later on, we're going to resume. The flow will be the same. Well, the flow is not the same, but what has been executed will be the same. So we have a first suspend, and then we have the resume. And after the resume, we're going to return over here. That's asynchronous completion. But we're going to see it in a real context later on. A more difficult example where we have two suspends and two resumes here on the right. That's a summary. We have a coroutine here with runs to completion. So that's the synchronous completion. On the right, we have the asynchronous completion where you have the suspend and the resume. So we see the four operations here in those slides, at least on the right. Now I have, that's all about coroutines. If you want more or better introduction than this one, a short introduction of 1 hour, I have some links to a good presentation of Andreas Fertig with PDF slides. So that's a reference for people who need more information or more background on coroutines. I have some technical notes over here that I'm going to skip because they are very difficult. It had to do with easy start versus lazy start. I'm in favor of eager start. And I have another presentation that's in the pipeline. It's not yet published. Be lazy or eager. For once, be eager because programmers are considered to be lazy, but for one time, I want them to be eager. At least the coroutines they write. Then that's a lazy start. It's much more complex than the eager start. And then there's another note about the return at the end. It's only specialists maybe who's going to see the difference, but I'm using a final waiter type on the left and not the one on the right. The one on the right has been introduced in terms of for lazy start coroutines, which led to potentially stack overflow. So this one on the right prevents it. That's all about coroutines and the introduction to it. Now something about synchronous and asynchronous programming. So that's the target of the where we're going to use coroutines for. So what is a synchronous or an asynchronous application? In my vision. So it's applications that using synchronous or asynchronous input and output. So synchronous is something like open, connect, read, and so on. Something we know for interacting with file systems or interacting with TCP/IP, where you have the connect instead of the open. You still have the read, the write, and then the close. Also, at a higher level, we have remote procedure calls, RPCs, or remote method invocations that can be synchronous or asynchronous. Also, the applications that are the target are applications that are usually long running. So you start them and they keep running for, let's say, forever until you stop the system. And they interact with the user, with the environment, or with other applications in the system. So if you have client-server applications, you have the client, the server, and they run for a long time, potentially. Also, applications that are single-threaded. So I want to introduce coroutines to make my application single-threaded instead of multi-threaded. It's something a client introduced 20 years ago. He wanted to get rid of all multi-threaded applications because of shared variables, and nobody knew which variables were shared by which threads. So at one moment they say we're going to rewrite everything and make our applications single-threaded. So that's something that's still stuck with me to that applications can be written single-threaded. A little bit in more detail. So the applications, they have to be long running with frequent input output to either a file system or to other applications. I also want the applications to be reactive, so they have to be able to react quickly to new input from the environment, which could be the user or from other applications in a distributed system. Difference between synchronous and asynchronous, it's important to know. So synchronous means that you're going to wait internally in your application for the response to every IO request. So you're going to send an open request and then only proceed when with your function uh, after the response has arrived. In an asynchronous application, you don't do that. You send out a request, and then later on, when there's nothing to do anymore, and you're ready to accept any input, you can also accept the response to your original request or even original requests if you have launched a number of them. So this application is not going to block him inside, so it should always be ready to accept new inputs, either responses to your original requests or totally new requests from other users. And we've seen that the advantage of a synchronous application, remember the first slide, is it's a simple style, it's easy to implement and maintain. The disadvantage is it's not reactive to new inputs, which may be unacceptable for many applications. The advantage of asynchronous and disadvantage are just the opposite. So in an asynchronous application, it is always reactive to new inputs. The disadvantage is the very fragmented programming style that we have seen on slide 3. So it makes it much more difficult to implement and maintain. So my question was, can we combine the benefit of both styles while avoiding the disadvantages? And that's something we're going to try to solve in this presentation. Something about the different styles of asynchronous programming. You can use callbacks. These callbacks, they can run on a separate thread or on the same thread. Uh, if they are run on the same thread as your application, you need an event loop. You can also use polling functions, which can be blocking or non-blocking. They return then when you need the result, you're going to poll instead of having a callback called back to you. So you need to poll explicitly at the time when you are ready to accept the response, when you have nothing else to do, for instance. Or you can even use events and messages at the lowest level, where you have an event loop which can pick up new events or which can also run the callback functions. So you see there are a lot of ways to implement asynchronous applications. A little bit about event loops. You can have them at one place in your application. You can have them at local places where you can say, now I'm going to wait for the local responses, let's say. Um, so you can never leaving event loops or event loops that are left after every event or message. So you see, these add to the flexibility of writing asynchronous applications, but they also add to the complexity because there are so many styles possible, and it's difficult to say that's the most efficient style to write or the most readable style to write. Maybe we can get rid of all those styles while turning to coroutines. So that's the question again at the end. Can we return to a single style using coroutines, pushing the differences to a library or framework level? Now, that's the main part of the presentation. I guess we're 25 minutes gone, something like that. Not even 20 minutes, just to have an idea. So I'm going to use several examples, going to skip the first slide. We're going to have, let's say, three major parts, looking at lower level input output, then upper level upper level, meaning a remote method invocation, remote procedure call, where you have 6 subsections. Yes, and then this section has grown in the past months. It's other uses of coroutines, using as an alternative to threads, and embedded software seen used in other programming languages like Python and C Sharp. We see a little bit about completion on another thread and so on. Now, let's start with this one. Low-level input-output with waits, write and read. Something we will see in, let's say, in boost ASIO, where you have boost, read at the boost input-output, you have write, read, open, close. These things you have to think. And here I have a wait, which can be synchronous or asynchronous. A wait that's synchronous is often called a sleep. So let's go into some more detail on this slide. I'm going to do this for this slide only. Other slides that will follow have the same similar, let's say, structure, but then I don't need to explain it in much more detail if I do this, if I do it for this slide. So we have on the left a function. We have a part one doing some stuff. Then it's going to wait for 100 units, whatever it may be. Let's say 100 is 100 seconds, and then part two. This means that function one is going to block its calling function, which can be in fact coming from the event loop for 100 units, let's say 100 seconds, which may be totally unacceptable. Nothing else can run in that time because function one, in fact, the call to the sleep is blocking the whole system. Now, if we do it with asynchronously, what are we going to do? Function one is going to call instead of wait, is going to call async wait, which is not going to block. It's just going to start an asynchronous wait function. It's going to pass a callback to it. So the 100 is still there. We have the async wait implemented here, and the communication framework is going to pass the callback. And the callback is in fact the part two that we find here on originally on the left. So what's going to happen here? Function one is called, going to start the async wait. It's going to return quasi immediately. So we have the return over here. And then we're going back to the event loop. Event loop is ready to accept any new input. And then after 100, well, it's here it's called milliseconds, but it could have been uh, seconds as well. After 100 time units, then there's going to be an event that's going to be scheduled. And we're going to call the callback over here with part two. We're going to return from here. So the same functionality will be executed, part two, part one, part two functionality. But this one, the asynchronous implementation is not going to block the event loop. So the application remains ready for accepting new inputs and then accept the response after the timeout. That's what we want as behavior. But maybe the implementation is a little bit difficult because, well, it's still a simple one because we had to split function one into two parts. Now, if you do it with coroutines, it's going to stay one block. We don't have to split it into two parts. It's one block, and you can even combine this into one line by writing co-wait st wait 100. The st stands for start wait, and this one is going to call async wait. So what's going to happen? We're going to start again the async wait, and then instead of having that split into two parts by the application programmer, we're going to suspend. But the suspend is going to return to the event loop. So the event loop is again ready to accept new inputs. Then after the timeout, so we may have processed new inputs in between, we are going to call this completion handler, which is going to resume. So the completion handler, you could say, it's something that I use as a name. It's a generic callback function. Generic in the sense that it's devoid or of any application functionality because the application functionality is still here, still in part two, and now it's also a template, so it's you can use different types. And then so this is going to resume, and then the resume is going to return. This part two is going to return over here. So what we see in this three pictures is the flow of asynchronous and the coroutine is almost identical. So we have the same control flow, but the style of a coroutine and the synchronous style with the function, that's almost also identical. Remember the first slide where they looked very similar apart from a few keywords. So the style of coroutine is the same as the style of synchronous, but the execution flow of a coroutine is the same as asynchronous, except that the programmer didn't have to didn't have to cut that original function into two parts, uh, pass second part as a callback function and so on. So coroutine should have an advantage over asynchronous style, and that's only a very simple application. Now let's go to, this is just explaining what was on the previous slide. So we can skip this one, the same over here. Comparison. Now it's a little bit more difficult. Well, difficult, we have a write and a read. Uh, that's all synchronous. We have the synchronous write, synchronous read. We have a write over here and an asynchronous read, because reading a response can take some time because the other one has to first respond, write the response to you. And then we have again a write and a start read and a call wait. It's a little bit more difficult, but again, you see the style of synchronous and coroutines will be very similar, but the execution flow of asynchronous will be the same as the execution flow of the coroutine. So we have the asynchronous execution flow, but with the style of the synchronous implementation. This one is with an asynchronous write and an asynchronous read. Uh, the synchronous part is still the same, so it's not repeated here. Here we had to split the function into three parts, or the application, right? I had to split it into three parts. Uh, Again, with coroutines, we don't have to split it. It's going to be the compiler who does the hard work, and the flow on the left and the right, the control flow is about the same. Again, this explanation. Yes, if you want to have the source code, just press these links. Everything that has been demonstrated or will be demonstrated either by diagrams or with explicit code fragments. The source code with the complete implementation, you can run them and you will see that the synchronous part, the asynchronous implementation and the coroutine implementation, they should have the same results, but with a different style of writing your code. Um, Now we're going to go to RMI. In fact, RMI, you could say at a lower level, is also using write and read, or even open, write, read, and close, because that's what you need for implementing um, remote method invocation or remote procedure call. This example is still small enough to have the code on one slide. So we have the synchronous style, the coroutine style. So I've put them side by side. So this example is still much more simple than the example we've seen on the first slide, but we're going to move to the more complex slide. So we have again the call return replacing the return, the async task recurring with int replacing the int, and then we have the call wait over here. The asynchronous part is a little bit more difficult. As you see, it's using also a callback, and it has some context to pass, because maybe you want to pass information from the front of your function to the end after the operation call, which is not possible when you split it in two parts, except you pass it as a context. So that's the context over here that can be passed to your callback function. So again, we see the similarity between synchronous and asynchronous and coroutine, and then the asynchronous style with the same behavior as the coroutine, but with a much more complicated programming style. That's the that code fragment, but then explained with the diagrams. So you will see again that the control flow is the same in the two right parts, the middle and the right part, while the writing style is the same or very similar in the synchronous and the coroutine part. Again, some explanation in text. So this I've explained while showing the diagrams and the code. So that's gone fast. Then we go to a call stack plus function. Yes, with one RMI. In fact, that's the first real world example, you could say. And it was in fact the starting point for what has become this presentation. So it was in 2022. I was a project, it was completely in C. It had this BLE stack implemented in C. And then I saw that you had a number of layers. So I have abstracted them, layer 4, layer 3, and so on. And each layer was passing a callback to the to the layer below. So you, layer 4 function called the layer 3 function passed the layer 4 callback to the layer 3 function, and so on. For layer 3 going to layer 2 going to layer 1. So that's code that I have seen literally in C, of course, with the real names instead of these abstracted names. But that, so we had the forward call going down was easy to implement, but then the response call was in fact a chain of callback functions where every callback had to be linked with the callback of the that was passed when we went down this control the protocol stack. It's something that I've seen let's say 3 years ago, but it's also something that's can occur in many implementations of protocol stacks, I suppose. It's not unique to that uh, specific project. It's a question that's around there for for a long time. How do we implement a protocol stack? So the layer 4 function, it goes to the layer 1, writing onto the physical medium, but it can't block the rest of the application. So afterwards, we have the callback chain going back upwards with the response. It's something you also can also find in device driver stacks, I suppose. So that was in fact the starting point of the whole presentation, what it has become uh, so far. If we put this in code, I have three functions where you have function 1 calling function 2, function 3. Function 3 is going to do a remote operation here with a write and a read. And again, if the write and the read takes some time, function 1 is going to block, in fact, the rest of the application because it can't return to the event loop. And maybe at function 1 doesn't see that at the lowest level, you have a blocking write and a blocking read. If we do it with asynchronous style, then the application programmer has to cut the original functions into two parts. See, we have these things here. Then we have a write, which is still blocking, may not hurt. We have an asynchronous read, which is not blocking. So here we're going to return passing control back to the event loop. And then when the response have arrived after X milliseconds, whatever, place event on the queue. And then we're going to do part two. So the part two flow is from right to left. Part two of function 3 is going to call part two of function 2. This is going to call part two of function 1, and then we're going to return to the event loop by here. With coroutines, we have this. I've used two lines because it's easier to have the flow illustrated with two lines instead of one line. But that's the only reason, because otherwise I would have too many overlapping arrows. So we have task 2 is equal to is coroutine 2, but we can put it in one line. You see the control flow of this one and the previous one is almost the same, or is the same, except that I explicit add a completion handle over here who's going to do the resume call. But that's just an implementation detail. But the style of this one is again the same as the style over here. And you see, it's like an animation. They map perfectly on each other. It's a last, it's an accomplishment to put these diagrams like this. So, in fact, also my first coroutine program I wrote, let's say in 6 years ago, looked like this. I had a coroutine calling coroutine 1, calling coroutine 2, calling coroutine 3. It went even a few levels deeper, and then they returned. So they behaved like this. And at that moment, I did not realize I had let's say, kind of solution for a protocol combination with coroutines. Now again, links to the code, the synchronous code, the asynchronous code, the coroutine codes. I even have some variants on it. So you have links to all of them, uh, explanation, and so on. Now, a function with three sequential RMIs, it's something we've seen before because that was the one that I've illustrated on slide 2 and 3. So it was a client who said, we're going to rewrite our whole, all our applications. They have to be, we're going to use only asynchronous communication all the way, nothing blocking, and applications have to be single threaded. And then they had a style that looked like this. So you have a start operation 1, and then you're going to pass to start operation 1 this as callback. So this function is first going to handle the results of operation 1 and then start operation 2. It's going to be passed this, oh sorry, this here as callback. The callback is first going to handle the operation 2 results and then start operation 3. So we have, let's say, a style that I call, let's see, is my machine needing some power? So we're going to have a style oh, that I can call a chain of callback functions. It's very fragmented. If you look at one function, because all these blue blocks are functions, then you see that a function is first going to process the results of a previous call, which may be somewhere else in another function that's not immediately in the neighborhood in your program, and then start another operation which may be unrelated when you just see that small block uh, as a whole. So it's a very fragmented style. It's you can recognize it even if you see the code from from a large distance, but it's difficult to maintain. It's also difficult to reuse blocks because they are all matched. They all have to match in the context of handling the result of one operation and starting another operation. So this block cannot be reused in another context very easily. This is the illustration when we do it with synchronous style. So we have part 1, calling a function, calling another function, and so on. This is when you do it with asynchronous style, where we have cut this original function on the left into 4 parts even, and then we have the coroutine style, where everything still remains one block of code, except that we have co-await, and instead of calling blocking operations, we call non-blocking operations. This is the code that we've seen on slide 1. We have the function 1, the coroutine 1, so it's the appetizer that I have used. And that's the operation, the asynchronous implementation that we've seen on slide 3. You see, it's much more difficult to read. And that's only a small one. Now as I said, for the asynchronous style, there are many variants possible. So the code you see on this slide will do the same as the code on this slide. It's still one function, but in fact, we have lambdas inside lambdas. So I can, and in fact, a lambda is a separate, the you could say it's still one piece of code, but it's very difficult to read. And also the execution is not going to be sequential as you may expect from um, from the synchronous style. The code again, or links to the code. Then we have parallel RMIs. That original example that I use here goes even back to 1987, but it's applicable to every system. Suppose we have code that you have 3 operation calls, but they can be executed in parallel because they are all going to different servers. But in the synchronous style, this one, operation 1, is going to block until response has arrived. Then it's going to call operation 2, which is going to block until the response has arrived, and so on. If you do this asynchronously, you're going to start the three operations one after the other. And then you may get a response of operation 2 before you get the response of operation 1, or and the operation 3 response may even be the first one to arrive. So you have to count somewhere that, okay, did I receive all responses? If you did, then you can execute part 2. So you see we have to cut the original function that we see here into different parts, uh, implement some functionality to count the responses, and then we can proceed with the end of the original function. With coroutines, we start them one after the other, and then we're going to use a when all, co-await when all with operation 1, operation 2, and operation 3, and we're going to go to part 2 once all operations have completed. So easy to write again, non-blocking, and yeah, what could be better? This is the code. So we have the function 1 that's blocking over here. This is the coroutine implementation. So we have those differences with async task over here. We have the when all. Then we're going sum, uh, to sum the results, like over here originally. This is the synchronous and the asynchronous implementation. I'm not going to read it in detail, but you see it's not that easy to read. I'm going to use here 3 lambdas. Yeah. Again, explanation in text for people who didn't follow the presentation, the video. Links to the call to the implementation. Then we have RMI inside nested loops. That's also based on a real example. It's from 4 years ago. It was implemented with Qt. I had to measure the round trip delay on a serial line, going from one computer to another computer and back. And to have some measure to have some, let's say, reliable results, what I did is I had 2 loops, a loop inside a loop. Uh, I produced messages of different lengths, and then for each of those messages, I've sent them a number of times onto the serial line and waited the response. And then I took let's say, the average of those different sends. Um, so we have a loop inside the loop to measure the delay for different lengths. With coroutines, it's easy to rewrite this over here. Again, this is not going to block, but suppose we have 100 message lengths, we're going to send it 100 times. So that's 10,000 times that we're going to have a delay for those operation calls over here. And this function 1 is going to block whomever called function 1 for doing these measurements. Here it's not going to be the case because for every co-await that we have over here is going to leave this coroutine, uh, again resume it, again leave it using a suspend and so on. So this coroutine 1 is not going to block the whole operation, the whole application. It's just going to be active at the moment a response has arrived and we can send a new response, a new request. So this function is this coroutine is going to enter, is going to suspend and resume about 10,000 times if you have 100 times 100. Originally, it was written in Qt 5 without coroutines, and I had to split up those double loops like it is, like here. So it's the code you have with you when you have to split up a double loop when you can't use loops, uh, because I was not allowed to block, or I didn't want to block the operation. Also, it was implemented with Qt and the Qt slots mechanism. So this is the code. It's hard to recognize that there's even a nested for loop in this. Again, links to the code. Then the last one, that's one based on the Bluetooth example where suppose at the lowest level you have to split up your functions into, you split up your messages into smaller parts, then in reality you have 3 loops. You have the one at the segmentation and reassembly level as well. Now that's part two here. I mean, yes. Then we have the other uses of coroutines. So you can use them as an alternative to threads. The original example is something that was, yeah, from 1985 even. So suppose you have a producer, which was, let's call it the business logic. So it has a loop here, it's going to do some operations, but from time to time it has to save information onto a disk. But in that time, we had the processor running this application did not have a disk attached. It was somewhere managed by another processor over a network. So, and it was a completely asynchronous system. So what they had to do, if you want to write something to disk, you have to open your file on disk with an asynchronous open. You have to start write, which was also asynchronous, and then you have to have to close, which was also asynchronous. So it was completely asynchronous system. And instead of merging this file write functionality with the original business logic, which was of course very well lead to a very strange style or a very unreadable style. They said we're going to launch another process or another thread, but at that moment they only had processes. We're going to launch another process, and that process is going to do the file write. So that process, it took the information to be written, opened the file asynchronously. Once it was open, it's going to start. Uh, it's going to write what had to be written. It's going to close. You see that I have already used the coroutine implementation, which is very clear because you have a well, let's say synchronous writing style. Um, and then you have the main application, which just has to say, look, I want to write this string, is going to be pushed onto a queue which is written by this file writer. So this one writes to a queue, this one reads to a queue, and as you can see, there's even a co-wait on the queue because the queue is also implemented as a coroutine or with functions that are coroutines. That's the main flow over here. Then we have this one over here. Yeah, that's the original. Well, it's based on the original Qt implementation. We have the measurement loop here where we have the double loop. Start reading. We have the prepare message. You're going to send a message. You're going to start reading and so on. So we have this double loop over here. But suppose you want to do those two measurements in parallel on two serial lines. Well, we have the measurement loop here, measurement loop 40. That's going to be started twice, as you can see. And then we're going to await the two instances. So these two coroutines, they are going to run not in parallel, but they are going to run in a cooperative way. So when this one has nothing to do, it's going to call co-wait, and this is going to call, uh, let's say, the control back to another one, to another loop, to the second instance of the loop, who can proceed. So that's originally you could say I'm going to call them, I'm going to run each of these on a separate thread. Well, that's not necessary with coroutines. Uh, you still have the original original style of writing, which is sequential, but because of the cooperative behavior of coroutines, it's like they are working in an interleave way, like you could have with threads, but then everything runs on one thread. Again, some more explanation in text, a link to the original code. So coroutines, they support cooperative multitasking. Threads support preemptive multitasking. So the question is, why can you not use coroutines as alternative to threads? Because they both support a different kind of multitasking, but at least it's multitasking they support. Also with thread synchronization, you have a lot of variants possible, CVs, condition variables, binary semaphores, mutexes, latches, and so on. Something you don't need with coroutines because nothing runs parallel. it's interleaved, so you don't have any variables that are really shared that have to be protected. So that's conclusion. You can use coroutines as an alternative to threads. In embedded software, that's something I did at the client. I saw, oh, you have a modern C++ compiler. It was ECC10. I'm going to use your code or hack your code. It was it was just a single application running on an embedded processor. Going to throw away everything that has to do with RTOS, which was free RTOS at that time. I'm going to insert a little bit of my coroutine code, and it ran perfectly on their processor. Um, don't need any operating system at all. If you want to use coroutines, you can use coroutines as a kind of alternative to FreeRTOS, to MusicOS, and so on, because they have some schedule, and you could say because of their cooperative multitasking. Something in other programming languages. In fact, that's I'm currently on a project with pipetting machines, so it's taking from this project. Uh, So what we have those pipettes here, those tips. You're going to first pick up those tips, then you're going to aspirate some fluid and dispense it at another place, and then you're going to dispose those tips. So you can see it's a mechanical stuff. It can take a few seconds to a few tens of seconds, but if you write it like this, it's in Python. You see, it's async and await. It's a synchronous style of writing. But pickup tips can take a few seconds. The aspirate of your fluid can take some seconds. The same for the dispense because those tips have to move to another location. The return tips can take some seconds and so on. But you don't have to worry. This function, liquid handling sequence, is not going to block the whole operation because everything is using await. Uh, it's something that's public domain. It's not tied to one company of pipetting machines, so it's or liquid handler machines. So I'm going to have a closer look at that code when I have more time. Currently, we don't use it, so I don't use async and await in Python, but I used it 2 years ago, 2.5 years ago, and I want to use it again, but I also want to use it in C++. Completion on another thread. Just how many minutes do I still have? Jens, can you give me an indication, please? Anyway, again,
Think like 5 more minutes.
5 more minutes. Okay,
How
thank
much
you.
more minutes do you need?
Oh yes, but okay. Um, so we have example with coroutines. No, it's not using coroutines. It's using a latch. What I want to say here is that if you have completion on another thread, you can have a synchronous style, even if you use an asynchronous uh, input-output system, but at the expense of blocking your application. So here we're going to start operation one. So it's going to call the operation one over here. So function one is going to call operation one over here at the top. Uh, it's going to start this operation, pass a callback function, which has a latch in between. The same, we're going to start operation one 3 times, as you see. That's operation one. We're going to start it 3 times, and then we're going to wait. So it's a very nice style because this one is synchronous, while these things, they are going to run in parallel because they are not blocking. So you're going to return quasi immediately from the three operation one calls. But then the blocking part is over here. It's in this wait. This is going to wait to block function one and everybody calling function one at this point at the main latch.wait. It's a nice style, but it's not perfect. If we do it at coroutines, we have about the same style over here. Yeah, I have added some more inputs and outputs over here that I didn't add over here. So I could get rid of them. Here we have the when all, the co-wait WA, which is in fact co-wait when all. But this co-wait is not going to block coroutine 1. It's going to suspend. So it's going to pass control again to the caller of coroutine 1. So the style now that we have with the asynchronous implementation is again a very sequential style, very close to the one that we have with pure synchronous implementation, and very close to the one we have with coroutines, except that with the synchronous with this implementation, we still have a blocking wait, not in the asynchronous input-output operations we call, but when we're waiting on the results. We don't have that when we do it with coroutines, because this one is going to say, I'm still waiting, I'm going to pass control back to you. Uh, this is an example of gRPC that you can find literally on the web. So it's not something that I have invented. It's literally taking from examples from gRPC, where you have say hello. It's going to say hello with the passing uh, callback function. You see you have a log guard here. You have a condition variable, and you have the CV log, CV wait log. So it's not something that I said, okay, I'm going to use this as a bad example. No, it's something I found on the web. And here you are going to block again. If you do it with coroutines, the start hello is over here. We're just going to co-wait it over here. And this one is going to pass control back to the caller. So there's no problem anymore with blocking. We again have the callback, but here I pass the completion handler that I've shown on previous slides. This is a more complicated example where we have, in fact, two asynchronous calls going to be started, a hello world and a route guide. So they are going to, it's a say hello and a get feature. They are going to be launched in parallel or one after the other. And then we are going to co-wait them by means of a condition variable wait with a counter. So it's you need to be more or less already a specialist, and it's maybe less maintainable. Also, it's code that runs in C++11. With C++20, you can use latches instead of having those low-level condition variables and log guards. Again, with coroutines, we only have that when all here. We're going to launch these things or call these things and wait them at one place. And this co-wait can again pass result to the caller. So no blocking inside. This It's sequential programming style, but we have avoided the blocking part. That's again a comparison where we have the CV wait, CV notify one. With coroutines, we have co-wait and the resume. Again, the code, if you want to see the code, yes.
Johan, resume is a wonderful way to say that we will continue this in another talk.
Yes, yes. Okay,
Contribution.
I'm going to resume quickly. So you see, there's some more examples, but everything you can find on the web. Made a comparison between these things here. Some more code. In fact, we have 4 different implementations. But anyway, I hope with these examples I have convinced you that you should definitely have a look at coroutines if you want to write a new application or you want to have asynchronous behavior, but without cutting your application into small pieces. Do it with coroutines. This last slide is from the manual of Dynamic C, where you have the one implemented with state machines and the one implemented with coroutines. So this code is more than, let's say it's 25 years old, and it was already available in a programming language or environment called Dynamic C. That's about all. Thank you. I don't have the time to say why you should not use coroutines. So you already know why you should use coroutines.
We do
Thank
have a
you,
talk
Jens.
for. Thank you. Thank you. And
Thank you all. Thank you, Jens.
yes. So if you have any more questions, Johan might be in the lounge after the talk. And with that, I'm going to end the stream. Thank you for your
Okay.
talk.
Thank you.